Right. Guys, while we are waiting for some more to join, can we please have any feedback on the homework? If there was any problems regarding the homework, especially the one on the multiplication of the matrices, and then we can continue. If you had any problems, or by a show of hands, how many of you have attempted matrix multiplication? Just raise your hand so that we can at least see. Okay, okay, all right. So if there's any problem regarding this, is there something you need me to explain? And so that we can at least quickly go through it before we continue with the rest of the lesson. Any problems, or was everything fine?
Everything was fine, sir.
Okay. Jay says how to do it. So please give me, you have to give me a question that they can at least go through. Then that would be how we will be explaining it, instead of just me explaining random things. Okay, there's a question of number 10 from Lloyd. Okay. So before I even start at number 10, I just want to, and Jay says number 8. Okay, so number 8 and number 10. Like those are the two examples I will do. I will do the answer for, and then we will see what it is we need to get. So I will start with number 8, then I will go to number 10, and then we'll see if we can get an answer from that as well. So in this case over here, we first check the dimension of the matrix. This is a 2 by 2, and this is 1 by or 1 by 3. All right. So this is 2 by 2 matrix because it has 2 rows and 2 columns. We are multiplying it by a 1 by 3, 1 row and 3 columns. So we first have to check this column and this row. If they are equal, then we can multiply. So in the first case, this is not equal. Okay, so this we can therefore not multiply. So this is not possible, or undefined, or impossible. Okay, not possible. Okay, so first one is not possible because it doesn't follow the rules. The rule is that the column of the first one and the row of the second one must be the same. So this is not the same, so we can therefore not multiply number 8. Okay, I hope that one is explained clearly to Jay as well. Pardon me, but I'm just going to quickly make use of the comments of this one because it will be easier to write as well. Just select another color. Okay, this is better. Okay, so for number 10, let's also do the same check again. So number 10, we have a 1 by 3. And in this one, we have 1, 2, 3. We have a 3 by 1. So we check the column of this one, and we check the row of that one. Are they the same? Yes, they are the same. So if they are the same, this means we can multiply them out. So our answer, therefore, would have 1 our answer will be just use the eraser quickly. Our answer will therefore be a 1 by 1, because this is a 1, which is going to be the one that we will have, and this is the other one which we are going to have. So it will be a 1 by 1, and a 1 by 1 also only means it's 1 row, 1 column, which means there's only one answer that will be the result of this multiplication. And this is also the beautiful thing about the matrix and how we can also learn from them. Okay, I'm gonna use this drawing because the other one is making funny things. Okay, so let's quickly multiply this one out. So we said we are going to multiply row by column, right? So we said for this answer, we will have the first element in the row. Okay, so I'll just make a matrix over here. The first element, which will be the 2 in my row, multiplied by the first element in my column, which is the -2, all right? That is what we have. And then we will add it with the next element. So the next element will be the -1 in my row, multiplied by the next element in the column, which is my 4, plus, we'll continue, the next element in my row is a 2, which will multiply the next element in the column, which is the 6. And that is what we have, and this will close the matrix. So we have to now simplify this everything together. So 2 times -2 is -4, plus 1 times 4 will be another -4, plus 2 times 6. 2 times 6 is 12. So I have -4 plus -4 is -8, plus 12. And please note these are all inside the matrix still. We just simplify. And this is also inside the matrix. So -8 plus 12 will give us a resulting matrix of just a 4. So Lloyd's answer of a 4, that will be correct. Okay, so this is why I said with matrices you have to practice. Okay, because if you don't practice, most of these things will be Greek. It will be impossible even to understand what's going on over here, and it will be a big problem later on if we try to even solve some of the things, because the answers they don't make sense most of the time if you don't follow the rules. Okay, so I hope that answers the 2 questions we had on the homework. And for those who didn't attempt it, please go and attempt it again. It will only benefit you more, and you will be able to have concrete questions that we can at least work through together. Uyama. Okay, so guys, if I would just ask you guys also to please rename your names to your school names or something like that, so that I at least know who it is we are dealing with, so it becomes easier. Okay. For example, Fluffy Mellows, Ujama, Pinky.
So Ujama is my school name.
Okay. Okay, Ujama. So Ujama, please don't write on the board. But Pinky and Fluffy Mellows, I don't know. I don't know who's Pinky and Fluffy Mellows. Fluffy Mellows sounds like Victoria things, probably. I don't want to speculate people's names and things in that regard. All right. Let's proceed with the thing. So please also, for those who attempted, you can share your answers or compare your answers with fellow classmates or friends, and we can see. So the other questions was fairly easy. It's just the last one is to check if we can multiply. If yes, we please multiply out, find the product. If no, then we cannot multiply it out. So some of these things are easy to note because we already told you some of the answers already. If it's not a square matrix and square matrices, that's the 2 by 2, 3 by 3. Those are the ones that we can normally multiply. But if it's equal matrices, same rows, same columns, or similar matrices, we normally can't multiply them because the rows and the columns will be slightly different, except for a square matrix. That is one way to look at it. Okay. Okay, so that one is Michael. So Michael, I'm just gonna rename you quickly. Okay. And thank you, Michael, for your comment. I understand. And I also noticed, yeah, just to talk about the activities. Yesterday there was a slight improvement. I saw a lot of people attempting some of the activities, which was actually good to see many more coming on board. And if you have problems at some of the things, I will definitely mark most of those things that you have submitted today, and then I will send it back to you. I also noticed very important that it is a good idea to upload files in PDF format. PDF is the ones I told you, those apps, if you are using your phone, in PDF format and not picture. In PDF format, it's like this document over here, and then I can easily just mark whatever you have on the document. Can you see like this? And when I close it off, then you will be able to see the marks that I've made on the work you have submitted. And that is a easier process. So if it's on the pictures, then I first have to convert them to PDF, and then I have to send it back to you later on. So that makes it a little bit slightly different and difficult. All right. Let's get started with today. Today I'm going to repeat what we talked about yesterday a little bit regarding the determinant of a matrix, because going forward we need to understand the determinant of a matrix as well. So we spoke about square matrices, and we talked about singular and non-singular matrices. And we spoke about that the singular matrices, we are talking about the determinant of a matrix is not 0, and the non-singular, the determinant of a matrix is not 0, and the other one, the determinant of a matrix is equals to 0. And then that will give us a singular matrix, okay? So by that, let me just, I want to write down here, this over here, this means the determinant, okay, is not equal to 0. Okay, so that is what this statement over here, I don't know if you can, if I can highlight it. This statement over here refers to, okay, so that's just the spotlight over here. So this means determinant of a matrix is not equals to 0. In vectors, this means the magnitude of the vector, okay? But in a matrix, we are looking at the determinant of the matrix, okay? So I want to re-explain determinant of the matrix again so that we just have a feel for it. This one means the determinant of a matrix is equals to 0. So that is the difference between a singular matrix and a non-singular matrix, okay? So if it's singular, the determinant is 0. If it's non-singular, the determinant is not 0. So not 0, if I just also emphasize on that, whenever you see something is not equals to 0, this means if you have your number line, right, 0 is here. So you either have negative numbers, okay, and or you have positive numbers. Okay, so any of this negative or positive numbers is not equal to 0. So that is what we imply by the determinant of a matrix. All right. So we normally use an example for a 3x3 one, because that's the most difficult one to do. But for you guys, you will be mostly focused on a 2x2. Okay. So it's mostly focused on a 2x2 square matrix. Okay. So, but continuing on, you will have to do a 3x3 next year, or wherever you find yourself doing mathematics again, if you are furthering your studies. Okay, so just to quickly explain how we get to a 2x2 and how we get to a 3x3, that is what I'm going to be doing now. So you can see there's a lot of numbers up here, and most of us, we don't know what those numbers actually mean or what they imply. So we just also want to explain some of them to you guys. All right, so if you look at the determinant of a 1x1 matrix, this is just, it's 1x1 is still a square matrix because it's one row, one column. Rows equals to column. That's what we call a square matrix. And for a 1x1 matrix, the determinant is just the element in the matrix. Okay, the positive value of the element or the element in that matrix. That's the determinant. Okay, and if it's a 2x2 matrix, so for the 2x2 matrix, we basically do a sort of cross multiplication of the elements in the matrix, and then we subtract the products, right? So this cross multiplication is what we want to focus on a little bit more. And let's look at a quick example over here. So let's say we have, I'm going to use letters here, A, B, C, D. Okay, so if we have letters over here, or we can have numbers as well. We can have 1, 2, 3, 4. These are the two ways. Letters is just showing that it can be any algebra form that we have. So normally we will say we have an abbreviation that we call the det. Let's say this is called matrix C, and this is called matrix D. So if we ask you for the determinant of C, and we ask you for the determinant of D, okay? So that is how we would write it in a question, right? Find the determinant of matrix A, find the determinant of matrix B or C or D, whichever one it is. So this again will have the following form. It will be the cross multiplication that we do. You will find some textbooks draw the arrows like this and like that. Okay, so they start with the A. We always start with the first element. That is what we have to do. So it doesn't matter which way you draw the arrows, we will still do the cross multiplication and then subtract. So the cross multiplication for, or the determinant for matrix C will be the following. We will have A, which is the first element, right? Multiplied by D, which is the element across it on the diagonal, minus whichever one you do, C multiplied by B. It will still be the same answer because it's multiplication. So we will minus the cross multiplications products of each of them. Okay, so this is how we will do it, and we will normally end up with a scalar quantity. That means a number value. So this is just like the formula we will use. And this is just the extra example that we have. So for D, if I have to do D, it will be 1 times 4. All right. And we normally put it in brackets because it's just a nice way of ordering it. And then the other one will be 3 times 2. All right. And then 1 times 4 will be 4. And then minus 3 times 2 will be 6. And 4 minus 6 will give us a minus 2. So this is one example that we can have. Please note that this method is irrespective of the signs. Maybe there was a minus there or there was a minus here. Then those minuses will still apply over here inside the brackets, and then we will do it. If there was only one minus, for example, only if the 2 was minus, so it will be minus 2 times this, then this will be minus 6, and we will put that minus 6 in a bracket, so it will be 4 plus 6, which will result in an 8. Okay, so you just follow your normal calculations as what you would normally be doing. Okay, so that is basically it on the determinant of a matrix, and we will be making use of the determinant a lot. So over here we have another example to find the determinant of a matrix, and you will see again we follow this the same rule. We will be doing cross multiplication. The 4 will multiply the 5, the 2 will multiply the minus 3. So we have 4 times 5 over there. This is the first bracket, minus the 2 times the minus 3, which is there. So 4 times 5, that is the 20, minus the 2 times minus 3, that will give us it will give us a minus 6. And if you remember the law of the brackets, minus bracket minus will give us a positive. So that will be 20 plus 6, and this will be 26. Okay, is it clear on the determinant, guys? Is there any problem here? I've explained it again from yesterday, because this is what we are going to be using continuing or going forward, calculating inverses of the matrix and so forth. All right, so that is it on the determinant. Just want to go back to today's work so that you can see what we have covered so far. So represent information in matrix form of any order and interpret the data. Okay, that is, we already did that. Calculate the product of a scalar quantity and a matrix. So matrix multiplication by a scalar, that we also did. Add and subtract matrices. So sum and difference. Sum is add, difference is subtract of any matrices not exceeding 3 by 3. We also did that. Products of matrices not exceeding a 2 by 2. So finding the product of matrices, we also looked at that. And use the zero and identity matrix. Okay, so zero matrix, we talked about it. Identity matrix, we haven't really touched on it so much because we want to explain it later on when we do the inverse of a matrix. But we have seen how a identity matrix looks like. And we said it's the one with the ones along the diagonals, all right, the main diagonal. That's what we have with an identity matrix. And then we say calculate the determinant of a matrix and the inverse of a non-singular 2 by 2 matrix. So we looked at the determinant. Okay, we have not yet done the inverse. All right, so the inverse is what we are going to be looking at next. But we first needed to understand the determinant on its own, and then after we do that, then we can now proceed. Hopefully by tomorrow we will be going into simultaneous equations, solving them by matrix method. So today we want to focus on inverse and identity matrices, how we will be making use of them as we proceed. Okay. Just to refresh everybody's mind, we had this identity matrix, ones going down the main diagonal, zeros everywhere else. And we showed you an example of the identity matrices, which is over here. Okay, so in most cases, we will be using this. This is for the 2 by 2. Okay, this one is for the 3 by 3. Okay. So this is the identity matrix. It's going to be the same all the time, every time, or everywhere. Whenever we talk about an identity matrix, it's going to be like this. Okay. For the 1 by 1, it's just the 1. Okay. And if you go on to a 4 by 4, then you just put more zeros, and then along the main diagonals, you just put a 1. Okay, this is called the main diagonal because it's starting from the first element, row 1, column 1, and then it goes in that diagonal there. That's why we call it the main diagonal. All right, so let's get into today's work now. I think I've explained most of the basics that we need to understand well, and we will now look at certain keywords and things that we will still now talk about. So we looked at singular, non-singular matrices and the determinant as well. We have not talked about the adjoint of a square matrix and its properties. Okay, so the adjoint is another one again that we need to look at, and then we will look at the inverse of a matrix and its properties, and then we will look at solution. This will be probably tomorrow, right? Solutions for simultaneous equations. All right, so let's get down to the crazy stuff. All right, so it is going to get crazy. This is just showing you if we have an x, if we have to find the determinants or solve for x using the determinants, we can also have these answers. Please note the following, that our elements inside the matrix are not limited only to integer numbers, 1, 0s. They can also be fractions inside the matrix. It's not limited to specific numbers or anything like that. So that is also important to note because some of the examples might get confusing later on. All right, so what we have over here is an example of an inverse of a matrix. All right, so a non-singular square matrix of order n is invertible, or we can get a inverse of it if this exists a square matrix B of the same order such that AB will give us an inverse of BA. Okay, so I'll explain what that means shortly as well. So let's just first get through this as well. So if a matrix A is non-singular, right? Remember we said we are looking for inverses of only non-singular matrix. Okay, so non-singular, that means that the determinant is not equals to 0. Okay, so you can see now how we are reading this this, how do I call it, expression or equation. We say the determinant of that matrix is not equals to 0. Okay, we don't now read it as the absolute value of A is not equals to 0, or the magnitude of A is not equal to 0. So this means the determinant of the matrix is not equals to 0. That's how we know it's a non-singular one. So first it must be non-singular, right? Then we can get an inverse. If the determinant is 0, we will not get an inverse because the 0 is what we will use to multiply the things inside, and then it will become a problem because everything will be 0 and we will end up with a 0 matrix. Okay. Then the inverse, now you can see again, the way I am reading this is now using English, but the way it's written, it's not in English, right? So if you look at this A minus 1, so we have the A minus 1, okay? And this is what we call the inverse. And then you have the other one that we used to do is the A prime, A with just the 1 on top. So A with the 1 on top is the A prime. I told you it's called a prime, and we call this was for the transpose, okay? This was for the transpose, okay? Where we change the columns into rows, rows into columns, something like that. So this was for the transpose of the matrix. That is what we were talking about. So now we are talking about the inverse, and the inverse is having a minus 1. In most cases, you will find it like this as well. So inverse, complements, those are some words that have been used similarly or together, and that is what we have. So it says if it's a non-singular matrix, then the inverse exists, okay? Then there is an inverse. And it is given by the equation, the inverse equals to 1 over the determinant. Okay, let me write it down. 1, green is not a good color. So this over here means 1 over the determinant, okay? So we call the determinant det, okay? Det of A, like I said before. So 1 over the determinant of A. So we know now how to calculate the determinant already. It's the cross multiplication and then we subtract it, okay? So once you get that answer of the determinant, you will put it here as a fraction, all right? And this dot means multiplied by the adjoint of A. So the adjoint of A is something that we haven't spoken of yet. So we have something called an adjoint. And we will look at the adjoint there. So the adjoint of A. So that means the matrix, the adjoint of matrix A. And this is how we will be applying the inverse formula all the time. So to get the inverse, you will be doing a lot of calculations. Remember, to get the, the determinant is a calculation on its own. To get an adjoint is another calculation on its own. Then you multiply these two calculations together. This will be basically a scalar multiplication. Scalar means this is a scalar quantity multiplied by the matrix that we will get, which is the adjoint matrix. And that will result in our new matrix, which we will call the inverse. Right? So there's a lot of calculations happening in here. And this is why I took it step by step to explain every single step what we have. So if you don't know what is a scalar multiplication, then it will be a problem again. So you have to go back to the previous lessons to find out how do we multiply scalar values with a matrix as well. Okay, so I hope I've done justice to explain some of the things that we will be seeing there. So now we have look at the steps that we have to do to find the inverse, because we said this is calculation, and then we must bring them all together. So we need to order them out in a nice way so that it becomes a little bit easier for us. So the first thing we need to do for the steps is we need to find out what is the determinant of the matrix, okay? And we already know it should be not a 0. And then we know that the matrix is invertible. Invertible means we can get the inverse of that matrix. And also we need to find out the adjoint of a matrix. Those are the two calculations that we have. And then we will multiply 1 over the determinant times the adjoint of that matrix. And then we will get our answer. So the examples that I have is a 3 by 3 matrix, but let's put in a 2 by 2 matrix. I did not do the steps with a 2 by 2 matrix. So I will write down an example of a 2 by 2 matrix over here. So we have, let's say 3, 4, minus 2 and 1. Okay, this is a matrix. Let's call this matrix B. Mind my writing, it might be looking crooked, but this is what we have. So this is a 2 by 2 matrix. Okay, so first we know it must be a 2 by 2 or a 3 by 3. Then we can find the inverse. If it's anything else, we cannot find the inverse. So the next step to find the inverse is we need to find out the determinant of B. The determinant of B must not equals to 0. So we first need to get the determinant and see if the determinant is equals to 0 or not equal to 0. So this will be the multiplication that we will do to find the determinant. So the determinant of B, which I will just put here in light green, will be equals to bracket 3 times 1 bracket minus bracket negative 2 times 4. This is the cross multiplication steps that we do to find the determinant. And therefore, this equals determinant of B will be 3 minus minus bracket minus 8. Okay, and that will be equals to 3 plus 8, and 3 plus 8 is 11. So obviously we know that 11 over here, 11 is not equals to 0. So we have a double check. Okay, so we check that, okay, the 11 is not equals to 0, and then that is now what we have to do. So bearing this in mind, I will now quickly talk about the adjoint of the matrix so that we can at least see how do we get the adjoint of the matrix. Okay, I didn't put in the adjoint of the matrix over here. So I think I should include it as well. All right, so I'm just going to clear this quickly now, and let's talk about the adjoint of the matrix. Okay, so the adjoint of a matrix in our case is going to be a little bit tricky in a sense that there is also steps involved here. So let me just list the steps for you. So we have step 1. Okay. So for step 1, what we will do to get the adjoint of the matrix is we are talking about a 2 by 2 matrix now. Okay. So for the adjoint of a 2 by 2 matrix, we are going to first swap the first element and the last element. Okay, so the first element is normally going to be Ij. Okay, I'm saying Ij or A row 1 column 1. That is the first element. Okay, so row 1 column 1 is a lot of words to write, so we just Ij it to make it simpler. You swap it with the last element, which will be Mn. All right, so we know that Mn is the one in the corner from what we have there. So swap means we basically we